Hey, this is Mr. Mitchell with a video. This one was primarily over electromagnetic waves. However, I do want to compare them with the mechanical waves that we have mentioned before. You may remember mechanical waves. You're generally looking at longitudinal waves like this that has compressions and rarefactions, and transverse waves, which has the crest and the trough and the amplitude and the wavelength and so on. Electromagnetic waves, even though they are not the same as mechanical waves, they do have that. Well, they're actually transverse waves, just in a different form. Don't confuse them with these mechanical waves, but the wave moves perpendicular to its direction, just like this one does. So just like this one, where the wave goes up and down and up and down, the direction of it is going forward, which is perpendicular to the up and down motion. And that's the same thing that's happening with these electromagnetic waves. You have up and down motion of the wave, but the direction is going forward, just like a transverse wave. So these transverse waves, however, in mechanical, they go through a medium. But in electromagnetic waves, they do not go through a medium. They travel through electric and magnetic fields. So what happens is you have a changing electric field, which creates a magnetic field, and a changing magnetic field creates an electric field. And you can have magnetic and electric fields without having some kind of medium like air molecules that the typical transverse waves would need. So these electrical and magnetic fields happen to be perpendicular to other, and that makes them look like a transverse wave. So electromagnetic waves, like I said before, do not need a medium, whereas mechanical do. And they travel at 300,000 kilometers per second, which is about 670 million miles per hour. Wow, that is fast. So when we think of mechanical and electromagnetic waves, one of the most common mechanical waves is sound, whereas one of the most common electromagnetic waves is light, sound, and light. So light, the speed of light is so much faster than the speed of sound, which is, about 767 miles per hour. However, electromagnetic waves are slower in solids and faster in gases and in no medium whatsoever. That's the opposite of mechanical waves. Mechanical waves are not slower in solids, they're faster in solids. They're slower in the liquids and the gases. So that is one distinction between mechanical and electromagnetic waves. Electromagnetic waves have frequencies and they have wavelengths, just like the other transverse waves do. Their range of frequencies are seen on the electromagnetic spectrum, which looks a little bit like this. The electromagnetic spectrum, we only see a small portion of the waves that are on the electromagnetic spectrum. You can see this says visible right here. But we utilize all of these. Radio waves, which have a very long wavelength and short frequencies, we use in radio towers. Microwaves, of course, we use in microwaves. Infrared cameras can pick up things that we can't see. Ultraviolet is like a black light, and X-rays, of course, we use in hospitals, and gamma rays are also used in hospitals. They're used to treat cancer. So gamma rays on this end have incredibly short wavelengths, which means they have a lot of frequency. And on this end, you have the radio, microwave, and infrared, which have incredibly long wavelengths, but have incredible short frequency. So which of these has more energy? Well, it would be up on this end. You may remember that electromagnetic waves The ones with the most frequencies are the ones that have the most energy. And that also goes to like visible light. I mean, we have red all the way through to purple, and the ones that have the most energy would be on this far side, on the blue and purple side. So they would have more energy than the waves coming in on the red and the yellow side. So we'll be working a little bit with the electromagnetic and with mechanical waves. Hope you've learned a thing or two. Bye-bye.